Buildzoid here, and today we're going to be doing another top-of-the-line RTX 4090 PCB breakdown, this time the MSI SUPRIM X, both the air-cooled and the liquid-cooled version. The PCB pictures are from techpowerup's review of the air-cooled and liquid-cooled SUPRIM X cards, so a big thank you to techpowerup for providing high-res PCB pictures. You can find more information about their about the cards in their reviews. There will be a link to both reviews down in the description below. And the first thing I think I'm going to address is the difference between the air-cooled and the liquid-cooled cards. So this is the liquid-cooled PCB from behind, because from the front they look exactly the same. And this is the air-cooled PCB. And it's a relatively large visual difference, but electrically speaking, they're actually exactly the same. So what's going on here is that these capacitors are, as far as I can tell, Panasonic pause caps, and they're 100 microfarad, 16 volt, tantalum polymer capacitors. And these are co-caps or KO caps. I'm not sure how it's supposed to be pronounced. I've only ever seen it on data sheets. These are made by Kemet, and these are 100 microfarad, 16 volt tantalum polymers. So that's the only difference between the air-cooled PCB and the liquid-cooled PCB. And honestly, I think this isn't even like an intentional design choice between the air-cooled card and the water-cooled card. It's probably just a case of MSI couldn't get enough. Like, I don't know who their preferred supplier for tantalum polymers is, but they couldn't get enough from one manufacturer, so they're dual sourcing them. Yeah, I don't think there's any other like big tantalum polymer capacitor manufacturers that I would expect MSI to use, or that I've seen them use. So yeah, so this really is just a case of like they probably couldn't get enough tantalums from just Panasonic or just Kemet, and so I would assume if you buy enough of these cards, you'll see that the like input filtering capacitors actually are kind of different depending on whatever was available when they were being manufactured. Anyway, so yeah, that's the only difference between the air-cooled card and the liquid-cooled card is just the and it's not really a difference. They're both like tantalum polymer capacitors. They're both 100 microfarads. They're both 16 volts. It's just like, yeah, different part suppliers. So it's like, yeah, it's not like there. It's not really a difference. It's just like visually it looks different. Electrically, it's like the same. Anyway, from the front, the cards are identical. So I've only taken one of the PCB pictures for the front of the card here. And I forgot to mention that we'll go over like non-power delivery features next. So we're going back to the back of the PCB because there's a dual BIOS switch on here. It has like two profiles, one which is like, I don't even think it's necessarily lower power, it's just supposed to be quieter, and the other one is like more like lower temperatures. But like you can check the techpowerup review for what exactly the BIOS switch does. But the main reason that you'd want a dual BIOS switch on a GPU is if you want to mess with BIOS flashing, various BIOSes, and there are quite a few different BIOSes available for 4090s. This takes out a lot of the risk of flashing a BIOS and then the card doesn't work, because you can just use the backup BIOS to boot the card back up and then fix the like flash over the other BIOS chip once you're in the OS. Anyway, so yeah, if you want to mess with like trying different BIOSes on your card, having a dual BIOS switch makes that a lot more convenient. Other than that, one of my favorite features on this card is that MSI is one of the few manufacturers to figure out how to put some fuses on a 40 series card. And admittedly, like, this is basically an issue of the 12 volt high power connector, because like historically, I think like MSI would put fuses on every single power input that they would have on like older cards. So like a 3090 from MSI, you'd have a fuse on every single power connector. Gigabyte would also put fuses on a lot of their cards on every single power connector. Asus did that like a really, really long time ago, but not recently. I'm trying to think. I'm thinking NVIDIA. I think Palette sometimes did it. PNY sometimes did it. So yeah, like various manufacturers would just have fuses on the power connectors, but recently MSI has been really consistent about having fuses for every single power connector, and that just acts as a like extra layer of safety for minimizing the damage that a potential like power delivery failure can cause. Now with the 12-volt high power connector, you can't really put a fuse on this connector because that connector is 600 watts. So if you want to put a fuse on it, it's going to be like 50 amps or 60 amps, and at that point that fuse is basically useless because it's never going to blow. So even so if you look at 4090s, I think Gigabyte's 4090 has a fuse on the PCIe because you can still, like realistically put a fuse on that. But the PCIe slot doesn't really power most of the GPU, so that fuse really doesn't have, like, it's not really protecting a whole lot. Or it's not so much, like, it's not really a very useful fuse in most scenarios. Um, and then they don't bother with a fuse on the 12-volt high power. And now MSI here as well doesn't actually have a fuse on the 12-volt high power because like all of the Vcore VRM, that just connects directly through these inductors and then these two shunt resistors and straight into the 12-volt high power connector. But because 40 series cards in general have a shunt resistor for monitoring the 12-volt power draw of the memory power delivery, the memory power delivery is on its own separate 12-volt circuit. And because the memory power delivery is on its own 12-volt circuit and it doesn't pull like 600 watts, you can actually put a fuse in front of it, which is a really good thing because memory VRM failures are generally catastrophic. As in, like, if you have like a Vcore VRM failure, they can be pretty bad. It can burn a hole in the PCB and then it's really awkward to fix and you need to like drill out however many layers of shorted PCB there are. So, Vcore VRM failures are pretty bad, but they don't tend to destroy the GPU. Memory VRM failures, on the other hand, have a tendency to kill memory chips and the memory controller, and the memory controller is part of the GPU, so if your memory VRM dies, bye-bye GPU, bye-bye memory. Like, basically the whole card is just spare parts at that point because the most expensive part of it, which is all of this stuff right here, that's destroyed if the memory VRM fails hard enough. So having a fuse, even just for the memory power delivery, in my opinion, is a really, really good thing. Because it drastically reduces the chances that the card will suffer a failure that just completely destroys everything. Or at least everything important. Like, you could still use it for parts, but like, it's not really, on a 4090, the power stages are like not really from a value perspective. That's not the important part that you'd actually want to protect. So I think it's like cool that MSI has this 20 amp fuse for the memory power delivery, and then also this 12 amp fuse down here for whatever the PCIe slot's powering. The PCIe slot's powering probably just like this voltage regulator, I'm actually not sure which chip is what for this. Okay, this is a buck converter. I recognize that part. I think there's another chip on the back. Yeah, so then we have this converter over here. And then it probably powers this. This is probably 5 volts just because it's kind of in the middle of nowhere. This might be more 5 volts. It could also be a 3.3 volt rail because NVIDIA cards for some reason regularly have multiple 3.3 volt rails. So not sure what that is. Down here we should have like 1.2 volts and probably 1.8. I'm not 100% certain. And then up here I think this is the PEX rail. So all of these minor voltage regulators, those almost certainly run off of the PCIe slot. So if any of those fails catastrophically, this fuse will sort of minimize the amount of damage that those can cause. These minor voltage regulators don't tend to cause the amount of damage that you would see from like a memory VRM failure. Like memory VRM failures are really, really bad. The vast majority of cards that I've seen where the memory VRM fails, just all the memory chips die, the memory controller dies, and like the card's basically just spare parts at that point. So this fuse isn't that important, but that one's easy to implement, so, you know, it's there. The 20 amp fuse that's on the like memory power delivery, that's a lot more useful. So yeah, that's one of my favorite features about this 4090, because it's like the only 4090 to actually have a fuse for the memory power delivery. And that's even though like MSI is using some rather fancy smart power stages that we will get to very shortly. So now let's talk about the big important power delivery. Vcore VRM is, in typical 4090 fashion, split in two, so that it can deliver power to the GPU core from both sides. This effectively doubles the cross-section of the power plane, right? Because you can have a power plane that's like this. And so instead of just having like this cross-section right here, you have you have twice as much cross-section, which reduces the power plane impedance, reducing the power losses in the power plane, also reducing, well, potentially leading to better voltage regulation. So this is just standard practice on modern high power draw GPUs because it helps the power delivery quite a bit. In terms of actual like phase configuration, we're looking at a rather wacky 12-phase VRM. It's controlled by this chip right over here. This is a Monolithic Power Systems MP2891. This is a 16-phase controller, but here it's running in 12 plus 4-phase configuration, which is standard for high-end 4090 PCBs that use this controller, that it runs in 12 plus 4. The 12 is for Vcore, the plus 4 is for the memory power delivery. If we go back to the front of the card, we have 26 power stages, which is why I said a rather wacky 12-phase, because yeah, how do you get 26 power stages onto a 12-phase controller? Well, that's really simple. Most of the phases have 2 power stages on them, and then there's 2 phases that have 3. And I don't know which phases those are. So yeah, but you can, like, this is actually kind of common on NVIDIA cards to not have perfectly, like, to not have all of the phases be the exact same size. All right, and that's been a thing since like the 2080 Ti, where on the 2080 Ti you had like an 8-phase Vcore VRM, but it had 11 power stages in it, if I remember correctly. So yeah, since the 2080 Ti, it's been pretty typical for high-end NVIDIA GPUs, or even sometimes even the lower-end NVIDIA GPU, like even mid-range NVIDIA GPUs will regularly have like 10 power stages running off of an 8-phase controller, where it's just like, yeah, 2 of the phases have an extra power stage in them. And then there's like some adjustment that needs to be done to the control circuitry so that that works properly, but that is typical for NVIDIA GPUs. Ultimately, this does technically make it, like having 26 power stages does technically make this the most powerful 4090 PCB, but I'm not sure that, like, with the phases all being like, with like 2 phases being like larger than the others, if that really is that relevant. Also, it's just straight up not that many more power stages than your like typical 24 power stage configuration that you see on the like other maxed out PCB configurations. For the actual power stages themselves, MSI is using a bunch of Monolithic Power Systems MP what are they? 86 957s. These are 70 amp smart power stages. And like most smart power stages, they integrate current monitoring, temperature monitoring, and also a whole bunch of safety features like overcurrent protection, undervolt. Well, the interesting one with these is that these actually have a like high side MOSFET failure protection mechanism. So that makes it even more so there's sort of like 2 layers of protection here, because I have heard of these power stages being able to actually fail and not disable the entire card. As in, like, the power stage dies and it just sort of turns itself off and it doesn't affect the operation of the rest of the card. So after like a power cycle, the card will actually turn back on with one of the power stages missing, which is really neat. But I've also heard of these managing to fail in such a way that the card actually stops working. So yeah, they do have a whole bunch of like neat safety features, but they're not, 100% reliable. So it's like, while these do have, like, these aren't your standard DRMOS components where, like, if a DRMOS component has the high side MOSFET fail, it's bad. Like, it's really, really bad. There's absolutely nothing to minimize the amount of damage that kind of failure will cause in a DRMOS component. Whereas in these, like, monolithic power systems have actually sort of added some extra functionality to try minimize the consequences of a high side MOSFET failure. But even that safety mechanism isn't 100% reliable, so, the fuse is definitely appreciated here. And honestly, it's kind of weird to see that combination of, like, these very advanced smart power stages and then still having the fuses, when, like, a lot of other 4090s regularly just use DRMOS components and don't even bother with any kind of fuses whatsoever. Anyway, so yeah, lots of safety features, all the typical monitoring functionality that you'd expect from and I think these might have a public data sheet, or there's like other power stages in monolith. Like, if you want more details about the various safety mechanisms that these have, you can find. I'm not sure if this specific power stage, but you can find other monolithic power systems, smart power stages with all of that functionality. They have public data sheets for them. It's just not this specific part, but these all. Well, I'm not sure if it's not this specific part. I don't know where I got my data sheet for these, so it might be public. It isn't, but there are definitely public ones that cover all of the extra, like, safety functionality that monolithic power systems, smart power stages have. I think Infineon also has some similar functionality, but I've never heard of that actually. The thing is, I don't think I've ever heard of the Infineon power stages failing in the first place. They also aren't very common on GPUs, so, that might be part of that. Anyway, so, yeah, we've got rather fancy smart power stages. These are actually not that rare for NVIDIA cards. It's just, well, like, well, NVIDIA likes to use them on the Founders Edition cards, and then everybody else likes to use cheaper parts, except MSI, apparently. Anyway, yeah, so we've got those smart power stages here, and they are 70 amps, which doesn't really sound that high, because obviously there are higher rated parts, or higher nominal current rating parts out there these days, but these are still extremely efficient. And with 26 of them, yeah, this will have no problem powering the core even on LN2. So outputting 1.2 volts, which is rather high for a 4090 at 500 kilohertz switching frequency. VRM, and we are only talking about the power losses of the power stages, so not including the power losses in the inductors or in the actual power plane itself. Outputting 300 amps, the power stages should produce only about 24 watts of heat. So that is literally less than 1 watt per power stage, right? Because there's 26 of them. So that is less than a watt per power stage. This card should actually be able to basically this should be able to run without a VRM heatsink. So that's kind of neat. Though I'm not sure. With the memory chip, well, the power plane might get kind of hot, but the power stages themselves really shouldn't be running very, very hot, because, yeah, like, this is a very low amount of heat output per power stage. Then at 400 amps, it should produce only about 30 watts of heat from the power stages. This might still work without a heatsink. Like, they might still be able to cool themselves passively. And then at 500 amps, we'd be looking at about 39 watts of heat. And at this point, heat sinks probably stop being optional. But we're also talking about current draws. Well, technically, you could hit this within the stock power limit of a 4090 with something like FirmArc. But that would also be at lower voltage, so the power losses should be a bit lower than at 1.2 volts. So that might still be... yeah, so, like... Not like this PCB will have no problem with like 500 amps output, especially like if you're, use the actual cooler that it comes with. And then 600 amps, we'll be looking at about 48 watts of heat. and then 800 amps. And this you're gonna need, you're gonna need to max out the power limit to hit that level of current draw probably. And 800 amps, now we're looking at like LN2 overclocking territory, about 78 watts of heat. And yeah, at this point, definitely the VRM is going to need, cooling of some kind. Though if you are doing LN2 overclocking, most benchmarks only last a couple minutes. So, there's also the factor of like, well, is the VRM going to overheat before the benchmark finishes? And these power stages do integrate like over temperature protection and everything. So the card should just turn off if the VRM gets too hot. Unless like they intentionally disabled the over temperature protection, which I hope they didn't, because that would be kind of silly. But anyway, yeah, an extremely powerful Vcore VRM on this card, which isn't really surprising considering that it's, MSI's top of the line PCB for a 4090. Now, for the memory power delivery, we're looking at more of the same power stages, right? And then it's a 4-phase, which is basically as powerful a memory VRM as you're going to get on a 4090. The memory VRM is spread out around the memory power distribution network. This just, again, same idea as with the Vcore VRM being split in two. It just reduces the impedance of the power distribution network for the memory chips. So lower power losses, maybe better voltage regulation. Yeah, pretty well, typically a 4090 will just have 3 of these, but this is a maxed out PCB, so they have all 4 memory phases populated. Now, in terms of capacitor configuration, this card, and we're going to start with the output filtering for the Vcore VRM. This card is like an interesting configuration, in my opinion, because the total capacitance here is actually rather low, right? So all of this is Vcore, and also MSI left a lot of unpopulated capacitor pads, right? And the funny thing is, it's relatively low total capacitance, but it's a lot of capacitors. So this has 48 220 microfarad SMD aluminum polymers from someone. I don't recognize this mark. I don't know which manufacturer uses these markings. It's not, this doesn't look like any Panasonic capacitor I've ever seen, so I don't think it's Panasonic. But I don't know who it is. So, but yeah, there's 48 220 microfarad capacitors, which is a lot of SMD polymers. That's the most SMD polymers in the output filter of any 4090 that I've seen. But because the capacitance per capacitor is so low, the overall capacitance here is actually not that high. So an interesting approach, because the total capacitance is relatively low, but there's a lot of capacitors in parallel. So in terms of ESR and ESL, this should actually be really, really good. And overall, I'd just love to see how this compares to a Strix on the oscilloscope, because the Strix has not that many fewer. Like the Strix is like 35 SMD aluminum polymers, but they're 470 microfarads, and then there's a whole bunch of CAN capacitors on top of that. So the Strix just has like a ridiculous amount of capacitance on the output, but it's spread across fewer SMD SMD polymers, and then there's like a bunch of CAN polymers that, and by CAN I mean the cylindrical ones. They're still SMD because they have like a SMD adapter, but yeah, that card has like a lot more capacitance, but should have like worse ESR and ESL relative to this configuration. But so it's like I'd love to see how these like the SUPRIM X and the Strix compare to each other on an oscilloscope, because it's like a very different, well, it's not very different, but it's a rather different approach. Like there's a lot less capacitance here than there is on the Strix, and it just kind of makes me wonder, is like, does the Strix just have way more capacitance than is even remotely necessary because Asus could, I guess? Or is MSI actually cutting corners with the capacitance here? Which would be weird, because they could have like added even more 220s, right? Like this is all unpopulated, this is all unpopulated, and then on the front of the card you have all of this, and all of this. Which even if they fully populated this with more 220 microfarads, it would still not actually be that much bulk capacitance, because the Strix is using capacitors that are like more than twice the capacitance of what this is using, but it would be closer. So yeah, we have a lot of capacitors, but individually each capacitor is actually like smaller than what you usually see on a 4090, and yeah, I wonder what that translates to in terms of actual voltage regulation performance. Now, behind the core, we have a pretty typical configuration for a high-end 4090. We have some 470 microfarad, what seem to be SP caps, so Panasonic aluminum polymers. And then, of course, we have some groups of multi-layer ceramics. I don't know what value these are. They might be 47 microfarads. They might even be 100 microfarads. That exists. You can get 100 microfarad 0805s. Yeah, I have no idea what these are, but this is a pretty typical configuration for a high-end 4090 where you have... and this is actually nicer than the minimum spec. I think the minimum spec from NVIDIA is that, like, you use 220 microfarads instead of 470 microfarads. So MSI has upgraded these a bit. The Founders Edition actually uses all multi-layer ceramics behind the core. But then if you look at the Strix actually looks very similar to this. So, yeah, ultimately, like, I don't see anything in, like, the total capacitance is kind of low. The configuration behind the core is relatively standard. I really wish I could measure this with an oscilloscope and compare it to some other 4090s also with the oscilloscope, because like this is so different from the other ones that it's like, on one hand, more capacitors in parallel should be better than fewer capacitors in parallel. On the other hand, there is not much capacitance here, and both of those factors like affect how the voltage regulation works out. So, and then it's also worth noting that, like, depending on how the VRM controller itself is tuned, you can get, like, you know, you could potentially see very similar voltage regulation from two very different capacitor configurations. So, yeah, like, very different from what you usually see on a 4090, but I'm not sure if it's actually better or if it's worse, because it's just so different. It might be, it might actually not make a difference. It's also a very realistic possibility, is like there's many approaches to end up with the same results when it comes to voltage regulation. So anyway, that's the Vcore output filtering, and like, I like the idea of having a lot of SMD capacitors in parallel, but then the 220 microfarads is like, that's kind of low. And yeah, I wish I could give you a, like, more substantial judgment, but I just don't know. Okay? Like, I just don't know. So anyway, let's talk about the memory output filtering, which is pretty standard 4090 stuff. Not comparable to the Strix. So we have some 470 microfarad, what seem to be Panasonic SP caps on the front of the card, right off of each of the memory phases. And then on the back of the card, we have some 220s mixed in around the memory chips. And this is standard. This is like basically what you would see on a Founders Edition, if I remember correctly. So yeah, the memory filtering is like bog standard 4090. Well, slightly better, because technically you can get some 4090s which will use like through-hole capacitors for part of the memory filtering, which through-hole capacitors are just worse than SMD aluminum polymers. So yeah, it's not like, when I say bog standard, I mean bog standard for like a high-end 4090 PCB. Yeah. So that's the memory filtering. Nothing really special there. It's less capacitance than, say, the Strix, but also memory power delivery doesn't tend to be as noisy as core power delivery. So this, again, might be in the realm of it actually doesn't matter. And yeah, like, so again, if I could, I'd measure it with an oscilloscope, but I can't. So I'm not 100% certain how much of a difference that makes, but that is like sort of the configuration here. Now, the input filter, on the other hand, on this card is actually kind of ridiculous. And honestly, I'm a bit confused as like about MSI's priorities here. So the input filtering for the Vcore VRM, because it's not shared, right? Like this inductor over here actually, right? Like if you look at how the power comes in, you have power comes in through the 12-volt high power, then it comes in through the 12-volt high power, goes over these two shunts, right? And then it splits off through this fuse and then through this inductor to the memory. And the idea behind this inductor is it basically blocks the switching noise from the Vcore VRM, or, well, this blocks the switching noise from the memory VRM from going like back to the 12-volt high power connector. And then we have these two inductors over here which block the switching noise from the Vcore VRM from going to the 12-volt high power connector. These are much lower inductance. These are 220 nanohenries, so these are very low inductance inductors. Also, they're in parallel because apparently just sourcing a higher current inductor was not an option. So yeah, so this is just kind of weird to see because usually if you have multiple, like usually you would see this for like per power connector kind of thing, but yeah, here it's just like they're in parallel because they needed the extra current handling capacity. But anyway, so these are basically here to sort of try block some of the switching noise from the Vcore VRM, and then also like the switching noise from the Vcore VRM won't like it'll get filtered partially by this input filtering inductor for the memory. So the memory's like input filtering is kind of isolated from the filtering for the Vcore, right? Like that's the whole point of all these inductors here. So I guess it's fair to sort of think about the Vcore filtering separately from the memory filtering, at least in terms of the capacitor banks. Anyway, so Vcore, you have all of these 180 microfarad can aluminum polymers, or cylindrical aluminum polymer. I should really be saying cylindrical. It's more accurate. Or like if I say can, I feel like somebody's going to think that's some kind of abbreviation when it really isn't. It's just like they look like a can. So, but anyway, these are aluminum polymers. I have no idea who makes them. They're 5,000 hours at 105 degrees Celsius. So, yeah, also they're 16 volts because they're on the 12-volt power plane. And then on the back of the card, we have all of the tantalums. And there is a lot of tantalums. And this is the thing that I'm like most confused about with this card is tantalum polymers are expensive. Like, really expensive. And for input filtering, they really shouldn't make much of a difference compared to the much, much cheaper cylindrical aluminum polymers, which is why I'm confused about them being here. Like, I can kind of get why you would use them, say, in this area of the card, because usually here you have clearance issues, like the heatsink, you know, you can't fit your cylindrical ones because they're kind of tall. But, like, there's space, right? Like, this isn't a particularly cramped PCB. I feel like they could have just put a second row of 180 microfarad caps behind the first row. Instead of all of the 100 microfarad caps that MSI, squeezed in on the back. But yeah, so we have a bunch of 100 microfarad 16-volt tantalum polymers on the back of the card as part of the input filtering. And yeah, I am like, basically the input filter on this card is like nicer than what you would see on, say, a 4090 Strix, but then the output filter is like significantly lower capacitance. So I really wish I could measure it I wish I could measure it. Because I find it really interesting how there's like these really big differences in the capacitor configuration between some of the top-end 4090s, where the manufacturers actually go and customize the card instead of just using the reference design from NVIDIA with varying amounts of components populated depending on how much money they felt like spending. So, yeah, the input filter on this is rather substantial. Interestingly enough, not fully populated again, right? Like there's all of this like over here where it's like, oh, apparently that was too many tantalums or something, right? And then you also have, okay, no, these are like 5-volt filtering, so those aren't part of the 12-volt filtering. So yeah, a rather interesting approach to the input filter, because it's like expensive the way that MSI's built it, and I'm not sure it actually offers any advantages over just more of these, right? Now, admittedly, in this area, maybe it's just like a clearance issue, but especially on this side, it's just like, why not more of the cheap ones? Because on the input filtering side of things, you don't really have to deal with the really, really fast transients that you have on the output of the VRM, right? So, yeah. And then for the memory, we just have a 100 microfarad tantalum per memory phase, right? Like you have one over here, one there, and one here. So nothing really special going on with that. Yeah, and for the memory, I actually get it. It's definitely a clearance thing, right? Just because of how the heatsink is designed, like you want your fin stack in this area, so putting cutouts for like a capacitor sitting over here or something, I can get why we're not seeing cylindrical capacitors for the memory. But why the Vcore VRM has so many tantalums on it, I am kind of confused, because that just seems not really, that it just doesn't seem very cost effective. But then, you know, I haven't measured the card with an oscilloscope, so maybe this actually, like, helps. But, yeah, I don't know. An interesting choice. So, yeah, that's the 4090 SUPRIM X PCB. Technically, the most powerful 4090 PCB, because it has 2 more power stages than I think every other card out there. And they do use the same 17, well, okay, not the same as in like literally the same part, but same nominal current rating as all the other 4090s, so at least high-end 4090s. If you get a cheap 4090, you can get 50 amp parts. Yeah, so 70 amp smart power stages for, which is like normal for high-end 4090 PCBs. I do like the fuses. I'll mention them again. I do think just like, especially the fuse on the memory is like, we should see that more on cards, especially cheaper cards. I feel like should have a fuse on the memory, because having like all of this die because some $2 DRMOS component just gave up on life seems kind of silly. If you could have like a, you know, actually it's probably not even a $2 DRMOS component. It's like a $1 DRMOS component killing, you know, several $100s worth of GPU and memory chips because you didn't put $1, like actually a like less than $1 fuse on the memory power delivery, is just kind of, you know, that just doesn't seem very sensible. So yeah, I really, really appreciate the fact, like the funny thing is MSI has the nice fancy power stages with the extra protections, and then they still put the fuse on it. So yeah, that's cool. And then you have the dual BIOS on this. And then just really the only thing I wonder about is like the voltage regulation. Like I don't think it's bad. I don't think it's going to be bad. But I wonder how it compares to the Strix. Yeah, because it's a very different approach to the capacitor configuration from what Asus has. And Asus GPUs, in my experience, usually have very good voltage regulation. Yeah, especially if you compare it to like reference designs from well, anyone. Well, like the reference design from NVIDIA. So yeah, and I don't think this would be, you know, like I would expect this to outperform in terms of voltage regulation to beat most 4090s, but I do wonder if it's like, is it comparable to the Strix? Is it slightly worse? I wish I knew, because it is very different from how the Strix is set up. And anyway, so yeah, that is the MSI RTX 4090 SUPRIM X air-cooled and liquid-cooled PCB, right? Because again, the only difference here is the brand of tantalum polymer capacitors between the two PCBs. So yeah, that's it. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, hoodies, posters, you know, the usual YouTuber merch. and I've also got a Bandcamp. There's a link to that down in the description below as well. And that's it for the video. So thank you for watching, and goodbye.